Imagine throwing a ball. The harder you throw, the farther it goes, right? Now imagine throwing it so hard it never comes down. That's the basic idea behind rockets. They need enough power to overcome Earth's gravity. Of course, throwing a ball into space isn't really possible. Our strongest throws are nothing compared to the force needed to escape Earth's pull. But the analogy helps us understand the challenge. Rockets are like super-powered throws, aiming for the stars. Everything in the universe that has mass also has gravity. This fundamental force is what shapes the cosmos, from the smallest particles to the largest galaxies. Without gravity, the universe as we know it would not exist. It is the glue that holds everything together, creating the structure and order we observe in the night sky. Gravity is a force that pulls objects towards each other. This invisible force acts over vast distances, influencing the motion of planets, stars, and even entire galaxies. It is the reason why planets orbit stars and why galaxies cluster together. Gravity is not just a force, it is a fundamental aspect of the fabric of space and time. Earth's gravity is what keeps you on the ground and makes things fall. When you drop an object, it accelerates towards the ground due to the gravitational pull. This same force allows us to walk, run, and jump, giving us a sense of stability and balance. Without gravity, life on Earth would be impossible. It's also what holds the moon in orbit around our planet. The gravitational pull between Earth and the moon creates tides in our oceans and stabilizes Earth's rotation. This delicate balance has been maintained for billions of years, showcasing the enduring power of gravity. To escape Earth's gravity, a rocket needs to reach a specific speed called escape velocity. This speed is approximately 11.2 kilometers per second, or about 25,000 miles per hour. Achieving this velocity requires immense energy and precision, which is why rocket launches are such complex and awe-inspiring events. Think of it as a speed limit for leaving Earth. If a rocket does not reach this speed, it will not have enough energy to overcome the gravitational pull and will eventually fall back to the surface. This concept is crucial for space exploration and understanding how we can travel beyond our planet. Go slower, and Earth's gravity will eventually pull you back down. This is why precise calculations and engineering are essential for successful space missions. Understanding gravity and its effects allows us to explore the universe and push the boundaries of human knowledge. So how do rockets achieve these incredible speeds? It's a fascinating process that combines physics, engineering, and a lot of power. The answer lies in Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. This principle is fundamental to understanding how rockets work. When a rocket engine fires, it expels gas at high speed out of the back of the rocket. This is the action force. According to Newton's third law, there must be an equal and opposite reaction force. Rockets burn fuel in their engines, which creates a tremendous amount of hot gas. This gas is then forced out of the rocket's nozzle at high speed. This expulsion of gas generates a powerful thrust. The hot gas blasting out of the nozzle is the action force, and the reaction force pushes the rocket in the opposite direction, propelling it upwards. The force of the gas escaping downwards creates an equal and opposite force that pushes the rocket upwards. This is how rockets are able to lift off the ground and travel into space. It's like jumping off a skateboard. You push down on the skateboard and it pushes back, sending you flying. In the same way, the rocket pushes down on the gas and the gas pushes back, sending the rocket soaring into the sky. Engineers and scientists meticulously plan every aspect of a rocket launch, from the amount of fuel needed to the precise angle of launch. Every detail is crucial to ensure the rocket reaches its intended destination. Once in space, rockets can deploy satellites, deliver supplies to space stations, or even carry astronauts on missions to explore new frontiers. The journey of a rocket is a testament to human ingenuity and the power of physics. Section 4, Reaching for the Stars, Staging the Climb. In this section, we delve into the intricate process of launching a rocket into space, a feat that requires meticulous planning, engineering prowess, and a deep understanding of physics. Launching something into space is hard work. It involves countless hours of preparation, testing, and coordination among various teams. Engineers and scientists work tirelessly to ensure every component of the rocket is functioning perfectly. It takes a lot of fuel to generate the necessary thrust. The engines must produce enough power to overcome Earth's gravity and propel the rocket into space. This requires a precise mixture of fuel and oxidizer, which is stored in massive tanks. But carrying all that fuel makes the rocket heavier, requiring even more fuel. This creates a challenging cycle, where the rocket needs more fuel to lift the additional weight, which in turn adds more weight. This is where staging comes in. Staging is a technique used to shed parts of the rocket that are no longer needed, reducing weight and allowing the remaining sections to accelerate more efficiently. A multi-stage rocket is like a layered cake. Each stage is stacked on top of the other with its own engines and fuel. As each stage completes its burn, it detaches, making the rocket progressively lighter. Each stage has its own engines and fuel. This design allows the rocket to maintain high efficiency and reach the necessary speeds to escape Earth's gravitational pull. Once a stage uses up its fuel, it detaches and falls back to Earth. This process is carefully timed to ensure the rocket remains on its intended trajectory. This makes the rocket lighter, allowing the remaining stages to accelerate faster. By the time the final stage ignites, the rocket is moving at incredible speeds, ready to deliver its payload into orbit or beyond. Section 5. Slipping through the air, the shape of speed. As rockets blast through the atmosphere, they encounter another challenge: air resistance. Air resistance is like an invisible wall that tries to slow the rocket down. This is why rockets are designed with a special aerodynamic shape. Their sleek, streamlined bodies are built to cut through the air with minimal resistance. This allows them to reach the incredible speeds needed for space travel. Section 6. Orbiting versus escaping, two different dances. There's a difference between reaching orbit and escaping Earth's gravity completely. Orbital velocity is the speed needed to stay in orbit around Earth, like the International Space Station does. Escape velocity, on the other hand, is the speed required to break free from Earth's gravitational pull and venture into deep space. Think of it like this. Orbiting is like running around a merry-go-round, while escaping is like jumping off completely. Section 7. Space Trivia. Test your cosmic knowledge. Now that you're a rocket scientist, almost, let's test your knowledge. What is the escape velocity of Earth? Hint, it's fast. Can you name the largest rocket ever built? What happens to a rocket's mass as it burns fuel? Space exploration is a journey of continuous learning. Keep asking questions and exploring the wonders of the universe.